Okay, now I'm also recording the webinar. So the critical zone is the outermost layer of the earth that connects the groundwater to the vegetation canopy. And it's where all the hydrological processes occur. And so it can be viewed under an hydrological point of view with the functional hydrological layers. Do you remember that on the first day we talked about the pedological point of view? So we divided the soil profile into pedological layers. So there is the O horizon, then there is the A and B until the bedrock at the bottom of the soil profile. But now we see the importance of uh, the functional hydrological subdivision that controls all the processes occurring into the critical zone. And you can see from this nice picture that was taken from the publication of Brooks and colleagues in WRR that basically the water cycle happen into the critical zone, controlling all the processes such as drainage, infiltration, transpiration, groundwater recharge, and so on. And so, what's the framework in which soil hydrologies work? So basically, our final target is to gain hydrological understanding, which happened during all the decades, starting from the early 19th. So I took this plot and slightly modified. I took this figure from the publication of Sivalapan and Bloch in 2017. So I slightly modified this very nice figure just to present our framework. And so on how to gain hydrological understanding throughout the history of hydrology. So basically, we see that the actual understanding is sandwiched between the technological opportunities and the societal needs. So as you can see here, the hydrological understanding faces a breakthrough where the understanding is steep, and the rise from new questions posed by the society, and then this euphoria is followed by a temporary disenchantment in which no more findings are available during the years. And then new questions are posed by the society and so on. So little by little, there is some progress into the understanding. And so we started 1 century ago, more or less, with the empirical era, working into the laboratory, into the field, in order to understand the basic concepts in soil hydrology. And then we evolved throughout the history of this last century and also this century. And we also progressed across the spatial scale. So we went from the laboratory and also from the plot site up to the regional scales. And nowadays, in the last decades, you can see on the right, we are facing global problems. So at the global scale, where we are in the co-evolution era, meaning that all the processes are related together, and we are into an interdisciplinary system of understanding. So the opportunities given by the technological advancements are huge, but also the challenges requested by the society require huge and intense efforts. So basically, nowadays we live in the Anthropocene, where when the human footprint has a huge impact on the ecosystem services. And so we require a very advanced research for soil hydrology. But what's our strategy in getting new strategies in research, especially in hydrology and soil hydrology and soil science in general? So basically, we start from the observations, and then we gain big data, because now we are in the era of big data, and we apply models of different complexities. Can be statistical models, like very simple regression equations, for instance, or machine learning. Nowadays, all the students are falling in love with machine learning because they have availability of global data sets, such as remote sensing. Everybody plays with the Google engine to download large data sets of remote sensing data, vegetation data. But the problem is that the soil data are available in a large quantity only at the surface. But when we want to go deeper into the soil, data are scarce, are not enough. And so applying machine learning to only by using only the soil surface data can be challenging, because we get an understanding only on what's going on the soil surface. But if we want to go deeper into the soil, we must still go to the field, excavate the pits, collect the soil samples, install new sensors, and so on. And so we still require large efforts in terms of personnel, costs, time, etc. So this is the price. If you want to explore soil science, there is a large availability of data on the soil surface. So very nice machine learning, very nice ideas going on, but still it's related to the to the outer skin of the critical zone. But then if we want to characterize the entire critical zone, still we have to make huge efforts to gain data and then apply the machine learning, any statistical strategy or modeling strategy to get the understanding. And that's how new ideas pop up. So it's the feedback between data and models, data and machine learning. And this continuous feedback maybe will produce new methods that will be transferred to end users and stakeholders. So this is the framework in which we operate. And the research questions raised by the society now are concern global issues, such as the impact of global warming on the ecosystem services across the critical zone, especially those related to the hydrological budget, to the water budget in the soil, plant, atmosphere system. But then we want to see the impact of droughts and floods on the ecosystem services, the impacts of wildfires, of contaminant transport across the soil profile down to the groundwater table, for instance, which is very important. And so that's how we must combine data, models, and statistical tools in order to produce new ideas, new methodologies to be transferred to the society itself. And you can look at the Horizon projects, the calls around the European Union or from the NSF and so on. So they touch different topics that that raise concerns on the society, such as salinity, carbon stock, the impact of drought on the agronomic production, and anywhere in the world. So that's why it's very important to consider the research questions posed by the society and find scenarios and solutions. So talking about data, we in our research team at the University of Napoli, Nunzio and I are managing the Alento Hydrological Observatory, which is located in southern Italy, in the administrative region of Campania. The Alento, the entire catchment covers an area of about 400 square kilometers. And in the early 90s, the Alento Dam was built and divides the upper part from the lower part. So you can see the upper Alento River catchment with the black borders that covers about 1/4 of the area, about 100 square kilometers, and the lower part, which is more devoted to agronomic practices. There are mostly crops, and it's more a flat area before the Mediterranean Sea. We focused our research activities in the upper part, especially mostly in the upper part of the catchment, even though we carried out some analysis also in the lower part. In the upper part, I'm going to talk about very quickly about this story because it's very important to present ourselves, but also our activities to the community before doing the modeling exercise, just to understand the importance of the modeling exercise in soil hydrology. So we started by establishing an historical site called MFC1, which is represented by the red circle. It's located in the southern hill slope, mostly covered by agroforestry, crops, and sparse vegetation. In this historical site, we installed a weather station, and we carried out different research activities that ended up about 10 years ago when we started new research activities thanks to the collaboration with the Institute of Jülich in Germany that provided us 2 cosmic ray neutron probes and different sensors to be installed into the soil. And so we established 2 new experimental sites. One is MFC2, the yellow symbol close to the old site. And the other one is GOR1, is the blue dots. And they were instrumented with 1 cosmic ray in each site, 1 weather station, and wireless sensor network, and stream flow sensors in the outlet of these 2 catchments. So I'm going to show you quickly the 2 catchments. So you can see that GOR1 is densely covered by a forest of oak and chestnut. There is a dense under canopy. It's in the north face hill slope with very steep topography. The aquifer is very deep and the soil is loamy mostly. The area covers about 20 hectares, if I remember well. And you can see the position of the cosmic ray. You can see the white triangle surrounded by the wireless sensor network. Over 20 positions, we installed sensors at 15 centimeter and 30 centimeter soil depth to measure the matrix potential and the soil water content. Actually, we monitor the soil temperature, electrical conductivity, and permittivity. And from permittivity, we estimate the soil water content, as Nunzio explained in the first day in the soil water content webinar. And we use our own calibration law. So we went to the field several times to measure directly the soil water content, and we developed our site-specific calibration equation. These sensors have been working since 2016, so almost 10 years, together with the weather stations, the stream flow sensors, In MFC2, we have also a network of piezometers, which is not shown. And we also carried out isotopic measurements for almost 3 years. So we went to the field every 2 weeks to collect soil samples, plant tissues in order to extract water and do the isotopic measurements in order to measure the stable water isotopes. And of course, we collected also free water from stream flow, groundwater, and rainfall. Stable water isotopes are used as natural environmental tracers that can help us to gain more hydrological understanding of the plant water sources or to trace water parcel across the soil profile, for instance. And then they can be used as well into the modeling, as I will present in a few slides. And of course, we coupled all these monitoring activities with field surveys and laboratory measurements. And so here in this slide, you can see the measurements, the pictures related to the particle size distribution, bulk density, soil organic carbon, pH. Some of them are even not mentioned, calcium carbonate, saturated water content, saturated hydraulic conductivity, and especially the soil hydraulic properties via the evaporation method, the water retention function and the hydraulic conductivity function. In the lab, we measure these soil hydraulic properties by using the evaporation method. So we collect a relatively big soil sample, 12 centimeter high. We take it into the lab and run the evaporation method, and then apply the inverse modeling for the calibration of the parameters, as you will see in the next slides, in order to get the Van Genupten parameters or any other parameters of the equations that will describe the water retention function and the hydraulic conductivity function. So all these activities in the observatory must be integrated. So we have remote sensing, hyperspectral measurements by using drones or portable devices, or even on dry soil samples. We use sensors installed into the soil over sparse positions. We carry out isotopic measurements for environmental tracers, as I said before. We do the geophysical surveys to explore the deeper parts of the soil profile in 3D, which is a very, very unique tool to explore the soil, the soil subsurface. And of course, we couple all these monitoring activities with intensive field campaigns to measure the soil physical, chemical, and hydraulic properties. In all this framework, then, we try to dedicate efforts in the data fusion in order to understand data and use data in a proper way. So we have information on the vegetation and soil characteristics across the entire or almost entire critical zone. And then we try to carry out model simulations in order to do what? On one side, on one hand, we try to build vulnerability indicators that can be useful for the society, for the concerns of the stakeholders in the area of interest. And in these slides, in the next slides, I'm going to show you a couple of examples, such as the water storage and the transit time. Just going to mention a bit. On the other side, we can build scenarios or even solutions, such as the nature-based solutions. But especially scenarios of global warming, land use change. Land use change is even more rapid than global warming and has a huge impact on the water budget, especially at catchment scale, but not only at catchment scale, but also at a regional scale and even continental scale. So as you can see here, just a couple of slides indicating examples of interesting indicators that we developed with Nunzio. Here we have the soil water storage, which is the water, the amount of water stored into the root zone of the soil profile, and can be an indicator of vulnerability, but also of resilience, because it tells you how much water can be exploited theoretically by the plant in that specific soil position. So basically, if you work at the definition of the soil water storage is given in the nice figure on the right. So that is the water beneath the water retention function. So you have to solve the integral between two limits, the upper limits and the lower limits in terms of pressure head. And you have to know, of course, the depth of the root zone. If you work at plot scale, this can be quite simple to assess, because at plot scale you can measure, you can go directly into your site, collect the soil samples, go to the lab, measure the hydraulic properties and all the things that you have to measure. But if you want to assess this kind of indicator at a regional scale, well, it becomes more challenging. And so you have to resort to more simplified methodologies, as presented in the paper recently published in WRR with Nunzio. So if you want to go deeper into this topic, then you can read this nice paper. And also the transit time is another very interesting indicator, because it exploits tracer transport, and we can use as well the hydrological model to run several simulations. So the transit time is defined easily by the difference between the arrival time at a certain target position and the entry time. In this example, you can see that if you want to trace a water parcel originating from a specific event, for instance, the green bar, so the other black bar are rainfall or irrigation events, and we label only the green bar, so a specific rainfall event, by assigning a specific isotopic concentration or tracer concentration in general. And then we run the model simulation for tracer transport. And so we know by definition the entry time, but we, through the simulation, we will know that the arrival time at the, for instance, if we want to determine the drainage travel time, so we go back down to the bottom of the soil profile, we wait the arrival time of the water parcel originating from the labeled rainfall event, the green bar, and then we obtain the arrival time. And then, so by the difference of T out between T out and T in, we can determine the travel time. You understand that if we want to calculate the travel time from each rainfall event, you have to run the same number of hydro simulations, so in a repeated sequence. So you label one event per time. So you start from the first one and you label, and then run the model, and then you label the second one, and then the third one, and so on. And you calculate the travel time for each rainfall event. And you understand that in the end, you will obtain a statistical distribution of transit times that will depend not only on the hydraulic characteristics of your soil profile, but will depend on the upper boundary conditions or on the atmospheric conditions. So the travel time will be different in summer when, for instance, here in the Mediterranean area, in Campania, the summer is dry and with few rainfall events. The transit time will be different from summer to winter. In winter, we have a very wet season with frequent rainfall events of high intensity. And so closer rainfall times will produce different travel times than in the summer. I want also to highlight that the new version of Hydrus 1D, the version number 5, the one that requires license, is interesting because it includes new modules. And one of those new interesting modules is particle tracking. And so that makes very, very similar tracking of water parcels originating from each rainfall events. And so in the paper published in 2023, we compared tracers, travel times calculated from tracer transport and transit time obtained from particle tracking. Very interesting situation, but particle tracking is in the new version of Hydrus 1D that requires the license. Today, I remind that we are going to use the old version of Hydrus 1D, which is free for everyone. The same thing can be done also for assessing the travel time of nitrates. The difference between nitrates and isotopes is that nitrates are the result of chemical transformation. So basically you start from the nitrogen-based fertilizer, then the fertilizer turns into NH4, and then the NH4 turns into nitrate. And so there is the chemical reaction, and we have to take into account for that. And today we are gonna simulate the nitrate transport in our exercise. So in this other study, it's very important to consider also the agronomic practices, because it's very important on the amount and the timing of the fertilizer application on the soil surface. And here, as a result, you can see that in a 10-meter thick soil profile, you can calculate the travel times over different depths. So we obtain travel times at 3 meters, 6 meters, and 10 meters in a soil profile located in the Sele River plain in southern Campania, very close to the city of Salerno, which is very close to Nunzio's city. And so it's very, the tracers and solute transport can be used under different conditions, so not only for environmental tracers, so for things related to the impact of drought, but also for agronomic purposes, such as nitrate fate and transport up to the groundwater table. And we know that nitrate transport is of concern for human health. And so, again, the society requests us to at least gain understanding and propose environmental friendly solutions. So just here a quick overview of the model that we are going to use. So this is Hydrus 1D, and we in the previous 2 webinars, we Nunzio talked about the importance of the Richards equation and the hydraulic properties, and now we are going to understand why. So I just refer the most recent publications given by Jirka Simunek, that is the father of Hydrus 1D. But there are like many publications, and you can, of course, read the technical manual and many other. There are also even books with many examples and very nice applications of all types. As I said in the second day, you need to download Hydrus 1D. So you go to PC Progress, register or login if you're already registered, and download the Hydrus 1D version 4.17, which is the last free version available for download. Of course, there is also Hydrus 3D. Hydrus 3D with the last license, which is very interesting for other hydrological applications. So I highly recommend that for some studies, and which is very interesting because the Richards equation is solved numerically in a 3D domain. So if you want to go into the deep understanding of, for instance, a field, a relatively small plot, it's very nice to apply the 3D dimensional, the three-dimensional version of the model. Just to mention that Nunzio already explained very well the Richards equation that is used to describe the variably saturated water flow across a soil profile. It is based on key parameters and variables. So I just mentioned the volumetric water content, the pressure head, the hydraulic conductivity, and so on. You can see the S term, which is the sink term, which represents the root water uptake, as we will see later on. But the key information to solve numerically the Richards equation, of course, it's again the soil hydraulic properties, and they are two, the water retention function and the hydraulic conductivity function. Sorry, guys, if I stress on this importance, I repeat several times, because if we don't know the soil hydraulic properties, we cannot solve the Richards equation. Of course, we have to know other kinds of information, such as the atmospheric boundary conditions, etc. But the hydraulic properties are the fundamental functions that need to be known before applying the modeling. And so the model, if we have a soil profile and we want to run the water budget, we need to know the upper boundary condition, the lower boundary condition, and the initial conditions at time zero, because we must define this basic information. And of course, we discretize the soil into several nodes to ease the calculation of the Richards equation across the soil profile. And so we will see in Hydrus 1D that there is a specific window, and we have several options to set the upper boundary conditions, the lower boundary conditions, and the initial conditions. So for the upper boundary condition, usually the most widespread information is represented by the atmospheric boundary condition, but we have also other options such as the constant pressure head, constant flux, and so on. The same for the lower boundary condition, but here you know better than me that at 1 meter, 2 meters, 10 meters of soil depth, it is very difficult to measure the water content or the pressure head or flux, etc. So usually we resort to a simplified condition, which is the free drainage. That can be acceptable under specific circumstances. And the initial condition, of course, must be known or at least assumed. That's why we installed the sensors across the soil profile, because we, first of all, we must start from known conditions, and then we check across time if the simulations are close or far from the direct measurements provided by the sensors. I don't know if there are questions, or because I check also on the chat and on the question, but so far there are no questions, I think. I believe. Let me know if you need some clarifications by far, but so far it's quite easy to it's just an overall presentation before the exercise. And so the water budget, the basically from we must set the upper boundary condition. So we have the weather station where we collect key weather variables such as the air temperature, relative humidity, wind speed and direction, global and net solar radiation, and of course precipitation, which is the primary and the most important variable for some reason. And then we use the weather data to estimate or calculate directly the evapotranspiration. Now, if you in your weather station you have all the sensors to monitor the air temperature, relative humidity, etc., you can apply the Penman-Monteith equation, which is physically based because it's based on the energy balance. If you are under data scarcity conditions and you have only the air temperature, for instance, you can resort to the Hargreaves equation, which is the temperature-based equation. Anyway, we estimate the crop reference potential evapotranspiration, the ET0, okay, and then we must turn ET0 into crop-specific potential evapotranspiration, which is ETC, by using the crop coefficient Kc. Now, if you have a perennial vegetation on your soil profile, Kc might be constant over time, so it has only one value across time. But if you have an annual crop, such as wheat or maize or something, the Kc changes seasonally every day during the growing season, and it's 0 during the dormant season. And so we must know the Kc value. Can be tabulated, or you can take it in the scientific literature and so on. Then we must split the crop-specific potential evapotranspiration into potential evaporation and potential transpiration. And we use the leaf area index, which is again time variant. So we have to know the leaf area index, especially for annual crops, because again, it changes every day or at least monthly. If you have a forest, of course, if you have trees, they depend if they lose or maintain the leaves. And so if you can use one single value for leaf area index, or if leaf area index gets to 0 during the winter time, etc., etc. So precipitation and potential evaporation will be the elements in the upper boundary condition, so on the soil surface, acting on the soil surface. The potential transpiration will occur across the root depth through the roots, so through the famous sink term, which depends on the root depth, which can change over time as well, if you have, again, an annual crop. And it has a specific root distribution. And of course, then you have the soil hydraulic parameters. If your soil is layered, which is the case under real world conditions, so you have many layers, with different hydraulic properties. So this is the real world. And so yeah, we have to know the hydraulic parameters of each functional layer, as I said. And the output of the water budget, of course, is composed by the actual transpiration happening over the roots. And the actual transpiration is subject to the Fed's stress function. I will talk about it. So it will be, the potential transpiration will be reduced into actual transpiration depending on the stress that is controlled on the pressurized soil profile. Then we have drainage at the soil profile bottom, and of course, the actual evaporation that again will depend on a specific pressure head value as a threshold, and we will see about that. As I said, the calculation of the ET0 is referred mostly to the Penman-Monteith equation, as you can see here. So if you have all the weather data, you can use easily this equation that is very well described into FAO paper number 56, given by Allen et al. In 1998. And so there are all the options, all the equations, if you miss some data, if you need to do other things. But this equation is the benchmark equation, and we must refer to this equation as the best that we can do to estimate the crop reference potential evapotranspiration. And of course, we resort to the Kc factor to turn the ET0 into ETC in order to calculate the crop-specific evapotranspiration, because the grass reference crop is the famous alfalfa that is well watered under optimal conditions, but the ETC requires the knowledge of the crop factor, which is specific for our specific field situation. If we don't have, if we miss measurements of relative humidity, wind speed, net radiation, we resort to simplified equations like the Hargreaves equation, which is temperature-based. And so we need only temperature measurements. So it's very easy to install a thermometer to measure minimum, mean, and maximum daily temperatures. And so we can calculate easily the Hargreaves equation. And we are gonna do that in the famous Excel file that I'm gonna send you through email. And of course, there is also a term, the extraterrestrial radiation, the RA, that must be known and depends on the latitude. So if you are in the northern hemisphere, we will use the rho belonging to the latitude at 40 degrees, because we are in Campania, and so we are going to use the radiation term depending on the months of the year. But of course, there is also the table belonging to the southern hemisphere, so it depends basically on the latitude from the equator to the North Pole, and it changes a lot. The soil hydraulic properties that must be known can be represented by mathematical functions. So basically, the most widespread mathematical function is the Van Genuchten function in 1980. This is also the mostly known equation. So we use the famous parameters of alpha, n, and so on. There is also the Brooks and Corey equation in 1964, which is interesting because its simplicity is integrated by the use of the bubbling pressure head, which is interesting because it's physically, this parameter is physically based. And so this equation, which is very, very simple, is very, very interesting. There are many other equations proposed in the literature, such as the Kosugi equation, Russell, Gardner, and so many others, including also the bimodal equations. So there are like more complex equations that now last week I saw also the tri-modal functions was by the group of Durner in Germany. But in this exercise, we are going to stick to the Mangan-Newton equation. What is difficult is to measure the soil hydraulic properties. So basically, as Nunzio said, we go to the field, collect the soil samples, then go to the lab, run the evaporation method, or the multi-step outflow method, basically a transit state flow experiment under controlled conditions. Then we run inverse modeling to calibrate the parameters, and we obtain the soil hydraulic parameters. But this is very onerous in terms of efforts. And so we can do that at soil profile scale, at field scale, but of course at regional or continental scale is not possible to resort to laboratory experiments. Of course, we have also another option, which is based on the inverse modeling by exploiting the water content measurements or the matrix potential measurements or the tracer measurements by running inverse modeling, and so to calibrate the parameters again. But you can do that as well at plot scale. What happens if we must estimate the soil hydraulic parameters at a regional or even continental or global scale? We have to use the so-called pedotransfer functions, which are statistical tools of different complexity that resort to easily retrievable soil physical and chemical data, such as the sand, silt, clay, soil organic carbon, bulk density, pH, calcium carbonate, and so on. They are of different complexities. And here I highlight that the Rosetta pedotransfer function is implemented into Hydrus 1D. And so we are going to use that based on the knowledge of sand, silt, clay, and bulk density, and so on. But there are like different pedotransfer functions. Here I collected a list of available existing pedotransfer functions in the literature, and you can see that most of them are empirical. I reported only those empirical PTFs that rely on simple regression equations. Of course, there are many others using machine learning and advanced statistical tools, but of course, they cannot be reproduced. Only Rosetta, which is implemented in Hydrus 1D, and the European Union PTF proposed by Szabó in 2021. They can be implemented in user-friendly environments. But all the other PTFs that you see are based on equations, and most of them are empirical. The empirical PTFs are efficient as long as they are fed by site-specific calibration procedures. So if you are in your site and you collect soil samples for direct measurements of soil hydraulic properties, then you develop your own PTF or recalibrate existing PTF, but you have to use direct measurements as well to develop empirical PTFs. So this is the great disadvantage, because you require, over a large area, you still have to invest huge efforts in collecting soil data. In the last two PTFs, are very interesting because they are different from all the others. They are semi-physical PTFs relying on the particle size distribution, and they rely on the hypothesis, sorry, on the on the hypothesis of shape similarity. And between the particle size distribution and the and the pore size distribution. Yes, no voice. After some time, I lose my voice. Okay. These two PTFs, the Mohammadi and Van Closter in 2011, and the Arya and Eitman in 2015, they don't require calibration, optimization of empirical parameters. And so, as I said, they resort to the entire curve of the particle size distribution plus the bulk density. And so they are interesting as long as the hypothesis of shape similarity holds. I had fun in developing these PTFs both in Excel and MATLAB. So please let me know if you're interested in further exploring the impact of using different PTFs in land surface models for hydrological simulations. Okay, last two slides before gaining back my voice. The root water stress. So we said that it depends on the Fed's function, that in turn depends on key pressure head values, such as the wilting point, which is the H4, at which the alpha parameter of the FEDs, the alpha ranges between 0 and 1, as you can see on the y-axis of the plot, and reduces the potential transpiration into actual transpiration. The H4 is the so-called wilting point at which the plant wilts and might die, and at which the alpha is 0. And so the potential transpiration becomes 0. The H3 is the key information, is the key pressure head at which the alpha starts to get below 1. Above H3, the pressure head will be 1, so there will be no stress because alpha is a multiplicative factor to potential transpiration. These values and also the H1 and the H2 are given as tabulated values in Hydrus 1D depending on the specific crops, either if they are annual crops or even for some trees like lemon trees, as we'll see later on. There is also the option of using the Van Newton function instead of the FEDES function, but in this specific exercise, we are going to use the FEDES function. And finally, for the solid transport, I'm going to mention the fundamental equation for solving the solid transport, which is the convention dispersion equation that is again given by key variables and parameters such as the solution concentration, of course, the bulk density, volumetric solute content, volumetric flux, and so on. But in the dispersion coefficient, which is one of the key parameters, come into play the longitudinal dispersivity that must be set in Hydrus 1D, which is usually assumed as 1/10 of the soil profile depth, or otherwise can be measured or optimized in inverse modeling exercises. All the other parameters are given in the literature, so we are going to use literature parameters for the nitrogen. Okay, let me know if you got the file through the email. Okay, luckily most of you, the first answers are positive. Okay, okay. Okay, so next step is to open the file and share the screen. Okay, I think you see my screen because I see that on my other laptop. Okay. Okay, so as you can see, here you see the first table on the left between column A and E. You see the weather data ranging from the 1st of January 1999. Oh, there is another one not receiving. Okay. Uh, Okay, I'm sending the last email then. Okay, please, if you see other messages, if you can help me sending other emails to share the file, because otherwise I don't have any. Okay, so you see my pointer. I think it's moving. So the weather station contains the data of the temperature data, minimum, maximum, and mean. Precipitation in millimeters. The temperature is in Celsius degrees, spanning from January 1st, 1999, up to the last day of 2012. So the last day of December in 2012. So there are almost about 5,000 records of measurements, okay? In this other table, you see that you have the monthly data of that extraterrestrial radiation value taken from the big table, from the Hargreaves table. So we are in the northern hemisphere. At Campania is about at 40 degrees of latitude, and so we will take the radiation values in that specific row. And these are monthly data. So now, why we are collecting data for temperature and precipitation data? Because we want to set up Hydrus 1D upper boundary conditions. So we need to prepare the data for Hydrus 1D. So we need to prepare a table reporting exactly the precipitation data and the potential transpiration and a potential evaporation. Okay, so in this exercise, we will do only a very quick exercise in Excel in order to prepare this table and transfer the data. I recommend you to get ready also to use Hydrus 1D. Consider that this webinar is recorded, so if you miss something, of course, you can post questions on the chat, but also there is the opportunity to rewatch the video and follow that into another time. So the Hargreaves equation is this one, reported in here. It's very easy to implement. So we must, the only thing that we must be careful is that the units, because the ET0 will be reported in millimeters per day, but then in Hydrus we will prefer to use centimeters per day. So we have to remember to convert millimeters into centimeters. The same applies to precipitation. Why? Because why centimeters and not millimeters? Usually in Hydrus it's, I mean, it's the same basically, but you know, the soil profile, I personally like to see that in centimeters. It's a preference, okay? So we will refer to centimeters for length units and days for time units. Okay, so in order to apply the Hargreaves equation, we already have the mean temperature, the max and minimum temperature. So we must only assign the RAD value to each day. Okay, in order to do that, so most of the students like to do that manually. So basically here, if we have to report the RAD value, you see that in January, which is the first month of the year, we have to write manually 6.4, 6.4, etc., etc. And then in February we change that it must be 8.5, 8.6, 8.6, etc. So what we do is to use the VLOOKUP function. It's in English. So what you will see here in my laptop is my laptop is in Italian because I need to teach students in Italian. But the function in English is called VLOOKUP. Okay. So if you are using any other language, please refer to go to Google and ask Google what's in your own language. Okay, so now you will see that in my laptop it will appear with cerca verticale, it's in Italian. So this function, sorry, I'm gonna zoom it. And write quickly the function. So the first value, you see that there are 4 options. In my case, they are separated by semicolon. I don't know in your laptop, but you see beneath the function that there is the instruction for you. Okay, so the first value is the value that you must search. And it is exactly the month of the year that has to be associated with the value of this month. So we need to do a preliminary operation for that, because I forgot, of course. So we need to add a column here and call it month. And also here we need to add a new column, because the month has to be in a numerical format. Here it's very easy to write a numerical format because they are just 12 values. So when I find 1 here, I go to 1 here and assign this number. When I find 2, I want to get this other number. Okay, so here I express the date format into month, the month of the year. So in Italian is maize, but in English is of this number. And of course, I need to change the format of the cell without the decimals. And it will be 1 for January, it will be 2 for February, and so on. Okay, until the bottom of this column. So now I can apply the VLOOKUP function. So I go again, in Italian is cerca.vert. So the first value is this value, separated by the semicolon. And now you have to look this value into this matrix in this table, in which the first column reports exactly the month into numerical values. And on the right, you have the value that you want to obtain from this search. So basically, this table has to be fixed. I use the F4. You see the dollars around each letter, because you have to fix this table during the search, because this value goes down for each record. But these values have to be steady, so they don't have to move during the search. Then, what is the index? What is the column? Is the first column or the second column? I want the values in the second columns, because I want to get the RAD values. And then in the last option, I say false, because I want that specific value. If you write true, vero in Italian, it will approximate. So write always false. Let me know if you have doubts or if you have questions, but basically, if you run this function over all the records, you will see that in February, it will get 8.6 and so on. In March, 11.4, and so on. Okay, let me know if you are okay with that. I can wait just a bit, because now we have prepared the factors for the multiplication. Okay, Anahita is okay. Okay, perfect. If you have doubts, please let me know. Otherwise, I can go on with I mean, the calculation of evapotranspiration is very easy. It's very straightforward. Please, if you are in Europe, some of you have the comma as decimal separator. Please make sure that you have the point as a digital separator, because then Hydrus 1D wants the point and not the comma to separate the decimal. Okay, make sure that you have the point. It happens especially in Italy for sure. I don't know if it's in other places in Europe. So now we can apply the equation. So we have the ET0 in millimeters per day. And here, since I don't remember the equation, I take this one. So I get 0.0023 multiplied by Tmed is Tmin in Italian plus 17. Oh, sorry. T max minus T min the elevation of 0.5 multiplied by the famous radian term. The first cell is G5. Okay. Let me know if the first value that you get is 1.25. Should be okay. If everything is correct. Okay, and you should see the ET0 in millimeters. Oops. Per day. If you quickly plot it, you should see typical the typical evolution of the evapotranspiration. This is the potential evapotranspiration that ranges between 0 more or less and 7, even 8 millimeters per day, and it reaches its peak in during the growing season in the summer, and it's almost zero during the winter when the temperatures are very low. The solar radiation is kind of weak, etc., etc. So you will see this kind of seasonal cycle across the years. I don't remember how many years they are, like 12 or 13 or whatever. But this is just to check if everything makes sense for the community. Okay, now we have to split. Here we can remove all this material, or at least I will remove it. Oops, sorry. Here, add more columns. Okay, just to clean it up. Now we need to separate the ET0. Let's say that for just because we run out of time, we assume that the KC is 1, okay? For simplicity, because now this is a demo, so we can invent data. So our purpose is not to make something very realistic and precise, but it's to demonstrate and to finally use Hydrus 1D. So I don't want to waste most of the time. So the ETC is easily calculated by multiplying the ET0 by 1. Of course, I need to fix 1 with the double dollar. So I do that just to show the methodology. But now I need to split the ETC into potential evaporation and potential transpiration, okay? By using the Liffera index. And we assume that the Liffera index is, for instance, is 4, okay? We just invent the Liffera index, and we know that we must use this other equation from the slides. So we report this equation. I remember that by heart, but now. So the EP is equal to ETC multiplied by the exp function of minus. This symbol is a constant, which can be assumed as 0.463, okay? Multiplied by the Liffera index that we assume to be 4. And we fix it, okay? And so I get these other values. And the TP is just the difference between the ETC minus the potential evaporation. Okay, now I can remove that. Okay, so we said that now we need to prepare the table for Hydrus 1D because we need to turn the units into centimeters per day. And we need to report the precipitation, EP and TP in centimeters per day. So here we have P in centimeters per day, then EP centimeters per day, and TP in centimeters per day. Okay, sorry guys if I'm precise. Okay, here, so we just have to divide by 10. So I take the precipitation and divide by 10, and the same take potential evaporation and divide by 10. The same for transpiration, potential transpiration, and divide by 10. And then I extend. Oh, make it quickly. Make it close to the table. Do like this. Double click. No, it's faster. Otherwise, slow. Okay, are you with me with the final table? Oh, yes. Walter, so you have the equation in your Excel file. Okay. Okay, so now we can open Hydrus 1D. So I need to unshare my screen and get the full screen. So I'm gonna unshare the screen and share Hydrus 1D. Okay, I'm gonna share all the screens. So I hope you downloaded the Hydrus 1D. Because we are ready to use it. Okay, there you go. Do you see my screen? No, okay. Ah, okay, interesting. So I need to share this other laptop. Wait. Just gonna transfer the data on the other laptop quickly. Just give me 1 minute. Let's see if I am able to log it. Okay, I'm almost done because I need to change my laptop. Okay, do you see my screen now? Nunzio, do you see my screen? Oh, if share. Ah, okay, so I think you see my screen. You see Hydrus 1D, it's open like this. Okay. Oh, why I don't see shot. But if you see this screen, I think we are in the. Okay. So this is Hydrus 1D, and of course this view is a scene. I mean, nothing is on the gray window. This is a very nice graphic user interface. And so we need to open a new project. So basically in the browse section, we must set up the working directory. Okay. So before opening a new project in Hydrus 1D, it's necessary to go to the set up a new working directory, generate a new folder, and then all the files will be stored in that directory. So in this case, if you see, I'm going to store in the working directory. There will be folder, and so I will browse my folder and say OK. The name can be test, whatever, and then you can describe the simulation that you are going to run project. And we can say nitrate simulation here and click OK. So after we click OK, a new window will pop up, and this window is separated by there will be like two windows, a pre-processing window on the left with the input files and all the setup steps. And in the post-processing window on the right, you will see all the results, and you will see all the figures and plots of the soil water content evolution, the pressure head evolution, the soil hydraulic properties, the water balance, the details, etc., etc. And in the pre-processing window, so you do a step-by-step multi-choice option. So you go to the main processes and start saying to the model, what do you want to simulate in Hydrus 1D? So basically, of course, the water flow is a must, but also solid transport. We can simulate also heat transport, root water uptake, and CO2 transport. Here we have inverse solutions, so there is a parameter optimization internal to Hydrus 1D, but we are not gonna talk about it because it deserves a specific webinar. The inverse modeling is very complex, and I suggest to refer to the publications of Jasper Krug, for instance, or many other experts on that. So there are like there is a huge world around parameter optimization, but this is the case today. So today we're gonna invent our soil hydraulic parameters, and so we want to simulate water flow and solid transport with the first option, of course, standard solid transport. We have many other options, and I remind you that Hydrus has a very nice graphical user interface, and so you can click on the help window just to be assisted by the technical manual on your side. And so now it's a step-by-step procedure. So you have to go next, and you see that now you can go also to the previous working windows. So now we are in the geometry information, in which the length units can be set as millimeters, centimeters, or meters. And I told you that my personal preference is centimeters, but if you like, you can change this option. Then here you can set the number of soil materials, so the soil horizons across your soil profile. By now, we can stick to only to one fake soil horizon, soil layer, but then we will progress. We will add new horizons in order to make something more realistic. Here you can see that you have also the option to decline your soil profile. So if you put one, the profile is perfectly vertical. If you put 0, it's perfectly horizontal. But if you put a value between 0 and 1, it will be tilted. The depth of the soil profile will be 2 meters, so 200 centimeters. Okay. If we go next, so here we have to set up the time units in days, but you see that there are also other options that go from seconds to years. Here we have to, on the other window, there is the time discretization. So the initial time is 0. And we need to go to the Excel file to set up the final time. So we go to the Excel file. And check exactly how many rows we count. So we have 5,113 rows. And of course, we want to also turn on the time variable boundary conditions. And again, we give daily values across all the records. Okay. And we click on next. So the print information is important for the to visualize the output files. So here, for instance, in the number of print times, we can, for instance, set up 10 print times in which the results will be reported in detail over 10 print times. And we must decide which ones are the time that we are interested in. So by default, the entire record will be divided equally into 10 intervals, but we have the opportunity, of course, to select manually the 10 print times. So we say OK. Here we have other options. For instance, this one. We run Hydrus, and we must press enter to continue, or if we uncheck, we avoid this step. Next, the iteration criteria. Jirka says always to suggest to not touch it unless you are a good an expert mathematician, because all these parameters help solve the Richards equation numerically. And so if you want to go deeper into the details of the solution of the Richards equation, you just have to click on the help and then carefully change all the options. But basically, in common exercises, it's more than enough to keep these values as default values. And then next, so in the soil hydraulic model window, you can select, as I said, the most widespread mathematical function, which is the Van Genooten function. Here we have other options. There is also the modification of the Van Genooten equation, the Brooks and Corey, the Kuzugi, and then we have also the dual porosity for bimodal functions. So you have the Darner equation, the Darner 1994, that describes the bimodal function for water retention and hydraulic activity. And then we have other options that are very, very interesting, because we have the dual porosity modeled by different options. Click on the help, and you can use these models that are more complex and require more parameters. So if you have specific measurements, ad hoc measurements, especially experimental data that support this kind of complexity, then you can these options, which are of course recommended if the soil profile is subject to dual porosity or dual permeability situations. Then you can also use the lookup table, so you can express the soil hydraulic properties with the predefined water content, pressure head, and hydraulic conductivity values. You have also, finally, you have the option to use the hysteresis. Usually it is not so important, but in some situations it's very important phenomena to be described, because, you know, as Nunzio said last time, when during the wetting cycle, the soil water retention function behaves way, and dry cycle, the water retention function behaves in a different way. So this phenomenon can be important in some situations, and you can see the impact of hysteresis not only in the lab but also when you couple the measurement of soil water content and pressure head by using the sensors installed. And if we go next, so now we have to set our water flow parameters. So here we have several options. As I said, okay, if we measured our Van Genooten parameters, which are the theta R, the theta S, so this is the residual water content, the theta R. Then there is the saturated water content. Then there are the alpha and M that are shape parameters of the water retention function proposed by the equation. And then there is the Ks, which is the saturated hydraulic conductivity that usually measured in the lab. And there is also the connectivity tortuosity parameter, L, featuring in hydraulic function of the equation. So basically, we have as I said, we have the options. So we either collect the soil sample, take it into the lab and determine the soil parameters, or we optimize the parameters directly by using field data, usually soil water content and pressure head values. for the calibration of the parameters. Or we use, if we are desperate, we use easily retrievable soil hydraulic, soil properties, physical or chemical. There are like tabulated values. So there are soil parameters according to the soil texture class. You know that the USDA texture classes are 12. And so Hydrus gives the opportunity to change the parameters according to texture class taken from the table of Carcel and Parish. Or we can use the Rosetta PIDO transfer function. So we go into this tab, and it opens the window controlling calculation of the Rosetta PTF. So we can use the sand, silt, and clay as input, or we can add also the information on bulk density, and we can use other information. For instance, by default, if we know sand, silt, clay, and bulk density, and we do the input here, select the input here, we get the output on the other side, on the right. So if we invent, for instance, that the sand is 30%, the silt is 40%, and the clay, of course, is 30%, and the bulk density is 1.2 gram over cubic centimeter, we can predict the corresponding soil hydraulic parameters. And if we accept the values of these parameters, they will pop up into the water flow parameters in this row. Okay, there you go. So again, I repeat, if you have doubt, I used for sand 30%, for silt 40%, for clay 30%, and for bulk density 1.2. Okay, to get this kind of parameters. So I get almost 0.5 for saturated water content, and these values for the other parameters. Then I click Next, and I need to set up the water flow boundary conditions. So since I have the atmospheric boundary conditions with the surface layer for ponding water, and here I need to set up the maximum height, the maximum pressure head at soil surface. Usually it can be 0.5 positive pressure ponding, water ponding over the soil surface. And then I can set up the free drainage for the lower boundary condition. As I said, this is a simplified option, but is driven by lack of data and information in the deeper part of our soil profile. So you know that we set up a soil depth of 2 meters, and it's very hard to get the information, the pressure head or water content. But if I have measurement of pressure head, I can set up a variable pressure head option and set up the measured values of pressure head that I at the bottom. But usually we resort to feed the information at the bottom. And as initial condition, we set up the values in pressure heads. So for solute transport, you see that in the Excel file there is another spreadsheet called solute transport, in which I reported all the options just to make sure that we don't forget the most important setup. So we need to know that first of all we have 3 solutes to simulate, because we apply the fertilizer that will turn into NH4, and then the NH4 will react and will be transformed to. The pulse duration in days is not so important, so we can leave also the default value of 100 days. But if you want to go deeper, again, I suggest to resort to help, or you can go directly to the website here to Hydros 1D and go to the forum, discussion forum, to see all the questions that pop up. So if you go to support and go to discussion forums, you can see that there are so many comments and questions posed. So you can go to Hydros 1D old free version, write your keyword for question, or you can search here for all the questions that were published in the forum. So if you go next, then you have to set up the bulk density. Of course, it was 1.2. And the famous longitudinal dispersivity, let's say, can be 1/10 of the soil profile depth as a rule of thumb. So since we set the soil profile to be 200 centimeters, we can set it as 20. Nobody will tell us anything because we don't reproduce real world measurements, so we can invent data in this exercise. For the solid specific parameters, I remind that for the nitrogen-based fertilizer and the other two parameters, we can put these solid specific parameters. So we can put 0, 1.52, and 1.64. These are all taken from the literature, and you can check by yourself all the setup for the solid concentration. So if we go next, now we have to set up the solid transport and reaction parameters for the 3 solids. So the solid number 1 is for the nitrogen-based fertilizers. So we copy paste only the first row of each, because here I reported the 2 layers, 2 materials. But in this exercise, we have only 1 layer. So I recommend to select all the row here and copy paste anyway. And they will be the same for the 2 layers. So they are like always the same parameters for each solid in each layer. So copy paste, so Control C and Control V in Hydros. Next, again, for solid 2, I go to the Excel file and copy paste from the column KD since the column alpha. So Control C and here Control V. And then next, for the third solid, the nitrate, I go again to copy paste and take from KD. You see that for solid 3 in Excel, I indicated the meaning of each solid. So the third solid is the nitrate. So I go Control C after selecting the row and Control V. Okay, and I go next. And the new window will pop up for the boundary conditions for solid transport. So the upper boundary condition is set to be concentration flux boundary condition, just to make sure. Here you can see that I also put the screenshot. For the lower boundary condition, it's a zero concentration gradient. And initial conditions, of course, I put the concentrations in the liquid phase as in this option, default option will be valid. So I go next. And finally, here I have to set up the table for the boundary condition. So I have to copy paste the vertical vector for precipitation, potential evaporation. Oh, sorry. I have to go in time information and click on meteorological data. Okay. No. Oh, of course, because I needed to set up, sorry, in the main processes, I need to activate also the root water uptake. That's why I didn't see the transpiration in the boundary conditions. Okay, so sorry, my bad, my mistake. So in the main processes, you need to activate water flow, solute transport, and root water uptake. And click OK or next, just to check the time. Okay. Okay, and go back to the time variable conditions. Oops, here. Oof. I lost the values for some reason. Okay. Okay, let's quickly repeat the exercise. Sorry, but there you go. So for geometry information, again, I repeat again the exercise, so just not to be lost. So water flow, solid transport, and root water uptake. Then I go next. Length units, centimeters, 200. That, then days, and then I need to set up the number of days, which are 5,113, and the same for the time variable boundary condition. And then I go next, the 10 print times here, default is okay, and then next. Okay, for the solid hydraulic properties, we said that it's 40% for sand, 30% for silt, and 40, and then 1.2, and I predict, oops. Oh no, it was the opposite, 30, 40, and 30, predict, and accept, and then I go next. So atmospheric boundary conditions with surface layer with 0.5 at soil surface, then 3 next. 52 in the second layer, in the second solid. The third solids, and then here I have to copy paste the parameters. Solid. Okay. For the second solid, and here for the third one, the nitrate. These are all the reaction parameters that basically control the transformation. Guys, I'm gonna save this time. Okay. So boundary conditions as default here. Okay, here for the root water uptake model, we also use the FEDES function for the solid uptake model, and we recommend that there is no stress for the nitrate solid uptake by the roots. And so we put a fake high number for the third solid, the nitrate, that there will be absorbed by the roots without any stress function for solid uptake. And the same also for the NH4, so we can set up 100 as well. And here the root water uptake parameters for the FEDES function. We must choose our crop, which can be corn, because usually the fertilizer here is applied into the cornfields in April. We will see in the Excel file how to get the fertilizer amount and timing. And so if we select corn from in the database, the corresponding values for P3, for instance, will be, this is the wilting point, okay, minus 8,000, at which the plant is expected to wilt and reduce the transpiration and basically get the alpha of FEDES at 0. And these are the other pressure head values at which the transpiration starts to get below 1. The alpha starts to get below 1, and therefore the potential transpiration starts to reduce into actual transpiration. Then you can see all the other parameters that are also the first two parameters are related to the conditions under saturation, in which you can have also some stress because of lack of oxygen, and so you can go to the help and check, but this is not our case, so we are interested especially in the wilting point and in the values by which the transpiration starts to decrease and to be stressed. So the P2H and P2L mean that P2H means the stress starts under high transpiration rates, and P2L the stress starts when the transpiration rates are low. Here, for instance, if you go to the help, the two limiting pressure heads are set as below, and so the high transpiration rate is set here in the R2H, and the low potential transpiration rate is set as R2L. But by now we are going to use, and this is set as a default values, but you can of course change these thresholds and play a bit. Okay, so finally we come up with our table. Time, precipitation, potential evaporation. This is the threshold pressure head at which, below which the evaporation, the potential evaporation is stressed and becomes actual transpiration. Actual evaporation, sorry. This is the potential transpiration, and then in the C top one, this is the concentration of the first solid, which is the fertilizer concentration that will be applied in April. So first of all, and then I'm gonna, of course, explain the C top one. Then you will see the C bottom, the concentration of the soil profile bottom of the first solid. That, of course, is always 0. Now we need to copy paste precipitation and evaporation and transpiration. So we go to the Excel file, to atmospheric fluxes spreadsheets, and we go in the new table that we generated here, and we start copy paste. So we select the whole column, Control C, and then here Control V. Okay. Then the same for evaporation. Again, I select all the column for evaporation, select, and then Control C, Control V. And then I go to transpiration, I select the column, Control C, and then Control V, okay? Oh, I'm checking on, are you in this step? Sorry, I save, otherwise, okay. So now we need to set up also the C-top for the first solute, because we need to apply the nitrogen-based fertilizer in April of each year. So in the Excel file, if you go to the second spreadsheet in solute transport, here the agronomic practice, the amount that the farmer gives to the field in April is 195 kilograms per hectare. So these units have to be converted into, of course, into grams over squared centimeters in for Hydrus 1D, because the units need to be converted to the Hydrus units. So we need to do this calculation, because 1 hectare is 10,000 squared meters. And of course, you have to convert the kilograms into grams. So there is another 1,000 factors, and you need to convert the cubic meters into cubic centimeters. So there is another factor here for conversion. So you get this number, and the timing is April. Let's say that we want to apply these fertilizer only in the month of April during the year, at the beginning of the growing season. And here I calculated for you the C-top 1. So if you see the function, I don't know if it is automatically converted, because this is in Italian. But basically it says that when you see the month number 4, the April, put this number 0.00195. Otherwise, put 0, because we don't apply any fertilizer on the soil surface. So all we have to do is to select the columns C-top 1, Control C, and then Control V. Okay, you will see a lot of zeros at the beginning, and then in April you should see, on the 1st of April, sorry, we apply the fertilizer. Okay, sorry, not in the entire month of April, but only on the 1st of April, of course, because this is important for, let's say we apply it once, and then we need to make sure that there is also the application of, it's a sort of fertigation, so also irrigation of at least 1 centimeter of water, because the fertilizer need to infiltrate into the soil. So we need to make sure that in the precipitation column, Then we will take care. Then we first run the simulation, and then we will see what happens if we won't do anything. So now, for now, we won't do anything. We will see what happens to the solid transport. Let's leave like this so far, and let's go to the next, and then we will change the simulation later on. So we go next, and so do you want to run profile application? Absolutely, yes. And so this is the setup of the soil profile. I hope you see the window, so you see the discretization. By default, they are 100 nodes. We said that so far we have only one layer, so you see that the color is uniform because we have a uniform soil profile. Here at the bottom right of your window, you have the zeta. And so when you go back and forth your pointer, you see that the zeta changes. So now I am at the soil surface and zeta is a 0. And as long as you go down, zeta becomes minus, for instance, here, minus 50, and so on, until the bottom, which is minus 200 centimeters. So we leave the discretization as it is, even though it is recommended to, let's say, make it more denser at the top and less denser at the bottom. But in this webinar, let's keep things smooth and simple. Here, the initial condition, you can see that you can go visit each icon. So if you go to the initial condition icon, which is the light blue bar with the red arrow, so in the initial condition window, you set up and you can edit the pressure head in each node. So you go to edit condition, click with the left button of the mouse. You can see a hand. You can select all the soil profile by, it turns yellow. And then you can set up your initial condition with a specific top value and bottom value, and then you can change linearly in between. So you can change that the top value can be left at minus 100, and the bottom value can be set at minus 200, for instance. And so you can see the variation from minus 100 pressure head and minus 200 pressure head at the bottom, okay? Here, another very important setup is the root water uptake, root distribution. So if you now, so far by default is 0, so there is no vegetation because there is no roots. Roots are 0, so we need to edit the condition again and select from 0 to 150 because usually the corn, the root depth of the corn is the maximum root depth is 1.5 meters, and we can set up the top value to be 1, sorry, and the bottom value to be 0. So it means that the root density is maximum at the soil surface and decreases to 0 at the root depth, which is 1.5 meters, so 150 centimeters soil depth. And so you can see that the color is changing across the root zone and then becomes 0 in the bottom of the soil profile. It means that there is maximum root depth near the surface and minimum root depth near the 150 centimeters depth. Of course, this root distribution changes over time as a function of time, but in this case we simplify the system and we keep it constant. But consider that At the beginning, Hydrus gives you the chance to change root depth as a function of time. Okay, so far we simplify the simulations and keep root depth constant over time, always from 0 to 150 centimeters with this specific root distribution, which changes linearly from top to bottom. Okay, I don't know if there are questions. Were you able to? Okay, there are no questions on the chat. And so I think the root depth, the root distribution is okay. The initial conditions was easy to change. Here the materials are only one. The discretization here, in the discretization profile discretization icon, you can set the number of nodes. By default, they are 101. You can increase the number of nodes, which is good if for some reasons. I think the maximum number of nodes, I don't remember in the old version of Hydrus, I think it was 5 or 1000 or something. Here you can set up the density, so you can make this discretization denser on the top of the soil profile and less dense at the bottom of the soil profile. Here you can put the observation nodes, so you can insert the observation nodes at specific depths and until a maximum number of 10 observation nodes. So we can put an observation node at sorry, one at 50, one at 100, and one at 150. Okay, to delete this one. Okay. So I go to insert, and you can see the hand, and you can insert the 3 observation nodes, one at 50 centimeters, one at 100 centimeters, and one at 150 centimeters. Okay. And if we are ready and happy with this setup, we can close. On top right, you can say yes, save changes. Okay. And then, okay, in the soil profile summary, it is reported the initial conditions that we set in the graphical user interface. So you can see that the pressure head ranges between -100 and -200 at the bottom of the soil profile. And then the root density spans from 1 at the soil profile and 0 at the bottom of the root zone, which is 1.5 meters. Okay, there is a request. Thanks, Nunzio. Okay, now Wandi Magen asks, in Hydrus 1D, can root zone development be prescribed as a time-varying function, root depth and root density distribution changing through the season? If yes, how do I implement time-dependent root growth and uptake parameters? Okay, this is a very good question. Thank you for this question. Yes, the answer is yes, because you can go here. First of all, if you go to main processes, you can activate root growth. I didn't do that because I want to keep this webinar very simple, because you know that there are like shortcomings and difficulties in Jirka is very skilled in teaching Hydrus 1D because he does several classes throughout several courses the years. I remind you that in the website you can check for courses which are held usually in United States, in Europe, throughout the world. But basically, if you activate root growth, so the root depth will be changed, okay, as a function of time. So in the now I don't do that, but in the time variable, in the variable boundary conditions, a new vector will pop up with the root depth values that you can set up and you can insert manually, like in the Excel file, okay? The root distribution, no, I think you cannot change the root distribution across the time, but you can change the root distribution function. So we choose the simplest root distribution function, but there are many other functions that are more complex. So the root distribution can change differently, of course, across depth. So there are other functions that may be more functional to your situation. So I hope I replied to your question. So, but this is very important question because, of course, in our in each site of the plant, the crop characteristics are very site specific. Oh, and the next question is that by Paul. Yes, sorry, I sent the Excel file by email because I couldn't share it with the guests of this webinar. Can someone, if you post your email, it will be sent by some volunteer if they, and someone will help me to send the Excel file by email. Okay, so now we are ready to go because now we are in the last step. So there is, as I said, a soil profile summary table that summarizes the setup that we made. Of course, again, the setup is very simple, kind of fake, if you accept this word, doesn't reflect any real world condition. It's just a demo. But anyway, now we are ready to press the famous button, like everybody likes to do this stuff. So if you press the green button, you run Hydrus 1D. I warn that sometimes there can be difficulties in solving the Richards equation. So sometimes there are convergence problems, and the Hydrus 1D stops at a certain point when it is not able to continue to solve the Richards equation, which is solved numerically. So sometimes there are like shortcomings and failures in Hydrus 1D, and so we have to go back to the initial setup and change the setup somehow. Usually it depends on the soil hydraulic parameters. Sometimes it's some iteration criteria parameters or some. You have to check if the upper boundary conditions seems okay, the units are okay, the precipitation and the evapotranspiration are reasonable and realistic. So you need to check several things, but if you press the button and click OK, so you see that the model runs every day until 5,113 days. So now, so far it runs smoothly. Okay, very nice. Okay, so in my case, I got a positive situation because I didn't get any convergence issues, and so it finishes at the last day, and it asks me if I press enter, I can continue, and it shows the output results. Okay, now in the post-processing, in the right window, you see the steps to visualize the output. So the water balance components, the water content in the observation points, the profile information at the print times, the soil hydraulic properties, the mass balance information, the runtime information, and so on. Okay, let me know if you got any problem. If you get, if the hydro simulation interrupts at a certain point, it means that you set up, you use the different setup from mine. This is not important. You can still visualize the output until that failure time. So it's not, don't worry if you get failures, because first of all, this is just a demo. The most important thing is that you see the results, or if you see the full simulation, it doesn't matter. If you stop, if Hydrus stopped after 1 year, is the same. It's not at this step. Okay, so the first step is to watch the water content values, the pressure head values, the solution values in the 3 observation points. Do you remember that we set the observation points at 50, 100, and 150 centimeters of soil depths? So we go to observation points. Usually the windows pops up and tells you that the file is too big, but you ignore it because you want to visualize the nice simulations. And so first of all, the plot needs a legend. So the first window shows the pressure heads, so the H as a function of time. So remember that we simulated more than 5,000 days. So and Hydrus shows you the pressure heads over the 3 observation nodes that were inserted across the soil profile. But I don't know the colors, so I don't know the legend, so I'm gonna add the legend to help me understand if the black line belongs to the first observation nodes or something else. So I double click with the left button of the mouse, and I go to legend and I make it visible, okay? And I do apply. So I get the legend, and the legend says that the black line belongs to the first node, so at 50 centimeters. The blue line belongs to the second node, and so on. And the third line is the pressure head at 150 centimeters, okay? You can go next, and you see the water content, you see, over the 3 observation nodes, and you see that the water content has the typical cycle, seasonal cycle of the upper boundary condition, the atmospheric conditions. You remember that we are in a Mediterranean area where we have the alternating cycle of wet season, in which is dominated by frequent rainfall events of relatively high intensity and relatively low temperature, in which evapotranspiration is pretty low. And there is the dry season between April and October. Usually we split our hydrological year in 6 months per season. So the first season is the wet season, spanning from October, November up to April. And then the second season is the dry season, spanning from April, May up to September, October, the other 6 months. The temperatures are pretty high. The evapotranspiration is high. The precipitation is low, not so frequent. And so the climate is very arid, especially near the coast.
If you go on the mountains, the orographic impact on the precipitation is very, very important. And so in the Alento, for example, we get a more humid climate even in the summer with more frequent precipitation events because the orographic effect is very, very important, at least in southern Italy. I don't know in the other parts, but at least here where we observe and record climate data, we get very different precipitation patterns between the mountains and the coastal areas that are flat and much more arid in the summer. And so you can see this very nice cycle of wetting and drying across all the years that are, if you count the peaks, you count the number of years, could be 12 or 13. And you can see that, of course, the black line, the more you go towards the soil surface, the more that specific depth is sensitive to the atmospheric conditions. So you get more wetting during the winter and more drying during the summer. Of course, when you get the observationals near the bottom of the soil profile, the soil water content gets more smooth in the seasonal cycle. Any questions so far? And of course, if you observe this plot, it comes into my mind to compare the simulated water content data and the measured water content data at the same soil depth. So imagine that we have installed in that specific soil profile, we have installed both the soil water content sensors and the soil matrix potential sensors. And now we want to compare the water content, the simulated and measured soil water content and matrix potential at the same specific depth. And so we test if the simulations are close or far from the reality of what we observe in the field under real world conditions. And so you can test if your model setup is realistic. So far, not so realistic because we set a uniform soil profile, and that is not the case under real world condition. Usually the soil profile is layered. And so the soil hydraulic properties change in each layer because, of course, they depend on many phenomena, such as, for instance, there is tillage over the soil surface. Actually, the soil hydraulic properties change over time, at least near the soil surface, because they are subject to several operations in agricultural fields, such as tillage, plowing, irrigation, shrinking and swelling, and so on. So these are the real world conditions, but anyway, you can test and validate your model simulations by comparing the simulated water content values with measured water content values. If you go on, you can see also the water fluxes over the observation nodes. And of course, you can see the concentration of the three solutes. And you will see that for solute number one, you can see only a few entries. I will tell you why, the reason why. But anyway, we are interested in the third concentration. In the third, the concentration of the third solute, which is the nitrate, when the NH4 reacts and turns into nitrate, and we see the concentration, it's black at 50 centimeters, but we want to, of course, quantify the concentration at the bottom of the soil profile, which will migrate potentially together with drainage down to the groundwater table. So we are interested to see the temporal evolution of concentration of nitrate across the soil profile, and we want to see also the nitrate the root nitrate uptake. Of course, we will see that in another window, but we want to see especially the exit of nitrate at the bottom of the soil profile that will potentially migrate down to the groundwater table. In the second step, you can see the profile information at the 10 print times. So you have the depth of the soil profile in the y-axis, and here in the x-axis you have the pressure head or other variables that you want to evaluate. For instance, here you have the water content. Again, you need to put the legend. So double click and make it visible. Okay, and so you have at least an understanding that T0, which is the black line, sorry. Okay, should be able to, okay, not able to move somewhere. Okay, maybe here is more visible. And you can see that, oh, thank you. So there is a question. Check. No, okay, no request. And you can see that the black line in this case is the water content that we set up at time 0. Actually, we set up the pressure head spanning from minus 100 to minus 200 centimeters, but as a consequence, the water content is calculated through the water retention function, okay, across all the soil profile. So you can see the water content profile at the 10 print times, and so you can get that also the print times are important. So if you have specific profile observations in specific times, so it's better that you set the print times at that specific day of observation. And so you can check if your water content profiles or pressure head profile corresponds to the measurement that effectively was taken into the field, okay? And the same for the hydraulic conductivity, hydraulic capacity, water flux, and then for root water uptake, and so on, and all the things. And also for concentration, you see that there is concentration. I can shift the legend here. So if we don't see enough details of concentration, because we see only the concentration profiles of at T1 and T4 for some reason, if we want to go to zoom in here, we just have to reduce the range of concentration. So basically we have to go at 0.00001, okay? So we double click on the x-axis, and the scale we uncheck automatic, and we do that manual, and the maximum value can be set at 4 times 0 and 1, okay? And so we can visualize much better the soil the concentration profile at different print times instead of the situation that, okay? Oh, then we have the water flow. Also here, just ignore this message because we put too much things. Okay, now we have all the output of the water budget across time. So I remind that we simulated many years of simulations. So here we have the potential surface flux, which is basically the surface flux is given by the hydrological flux happening on the soil surface. So it's precipitation minus potential evaporation. Then if we go next, and of course, when you see the negative events, these are the precipitation events entering the soil surface because they are negative, they go downward. And when you see here, we go double click on the y-axis. If you zoom between 0 and 1, and you see that there are positive fluxing. So this is water exiting the soil surface through potential evaporation. And so you see positive flux. So upward, happening upward, okay? Okay, if you go next, you can see the potential root water uptake. So this is the TP that we set up and we calculated in Excel. Oh, thanks, Nunzio. I got another question. Let me see. Okay, is it possible to simulate the complete nitrogen balance in soil, including processes such as mineralization, nitrification, denitrification, and so on? Yes, the answer is yes, you can, but probably you need to use the other model that is coupled to Hydrus 1D. I don't remember the name now, but yes, if you go to the forum, for sure you'll find easily the answer, because probably if I remember well, you need to couple another model to Hydrus, a chemistry model that considers all those specific processes. What I show you is just the basic nitrogen cycle, considering only the nitrification until the final product that are nitrates. But yes, you can absolutely absolutely describe and simulate the complete nitrogen balance. If you go to the forum, now I don't remember, it's a strange name starting with the fee or something. So, but if you go to the discussion forum or to the technical manual, I'm quite sure that you will find easily the answer, but the answer is yes. Amor, why always potential values? Not always, only in, because when we go next, we will find also the actual. So I'm just at the beginning. So this is the first product output, which is the potential surface flux. This is the second output, which is the potential root water uptake that we calculated in Excel. And this is the actual, sorry, the potential transpiration. And now we have the actual surface flux. Actual surface flux means that it was, sorry, I have to go back to the, I think the minimum was around -7. Visualize on the precipitation. So of course the actual is very similar to the original potential surface flux. So the potential surface flux is what we imposed to the model in the upper boundary condition, and the actual surface flux is after the stress on the evaporation, or if something changes in the upper boundary condition according to the threshold that we set up in the pre-processing. And here we have the actual root water uptake. Again, we have to adjust. Once you do that, it validates for all, and you can see that if you notice, the actual root water uptake should be lower than the potential root water uptake. You can quickly check here that the potential root water uptake was higher than the actual one. Why? Because of the FEDS stress function. It means that, especially in the summer, I remember that we didn't apply any irrigation so far, then we will apply irrigation. Therefore, we simulated a rain-fed condition, no irrigation, but we know that in the summer, rainfall is not enough to satisfy the transpiration demand by the plant, by the crop. And therefore, the FEDS, the soil profile, the pressure head profile gets to dry conditions. And we know that under dry conditions, the alpha of the FEDS function gets below 1, almost to 0, almost to the wilting point. So the alpha is a multiplicator of TP, and you get the TA, the actual root water uptake. Okay, this is very, very important. Why? Because potential transpiration minus actual transpiration is the root water uptake stress. It's the theoretical deficit, water deficit that we should provide through irrigation to satisfy all the potential transpiration demand for the crop. Okay? Then we will see, after we apply irrigation, we will see that the irrigation a buffer, so limits the stress consistently and reduces and increases the actual. Yes, we don't see the bottom flux because I messed up with let's see. Okay, so we are at the bottom flux. You see this nice figure showing the drainage. Negative drainage because it's exiting the soil profile downward, so it's downward flux. So this is potential groundwater recharge. And of course, it's happening in the wet season. Not all the wet season, because some wet season can be can rain less than normal if we consider only statistics of wet seasons. But basically, you can see this sort of again seasonal cycle, and so we have. Oh, there are other questions. Thanks. So, Isai asks, for soil column experiments where urea is injected as a source of nitrogen, is a sea bottom the concentration of nitrogen species in the effluent? Yes, in the column experiments, laboratory experiments are completely different from field experiments. So consider that it's under controlled situation. So you control both the upper boundary and the lower boundary conditions in terms of flux and concentration. And so you can easily set this experiment in Hydrus 1D because you can easily set the control on the upper and lower boundary condition. Okay, so it's completely different from the field in which the lower boundary condition is unknown, and therefore we set simply free drainage, which is a sort of pseudo-realistic simplification. But in laboratory experiments, yes, you can control. So you are under control conditions, and therefore you can set up an optimal setup of model simulations in Hydrus 1D. I don't know if I answered, but if you have other doubts, you should consider that there were many publications available on this topic, so you can search easily in the literature what the other scientists did in the past, because this is a very common situation. Okay, and after the bottom flux, we have the now the cumulative, all the cumulative fluxes. So just I'll go very quickly. So again, this is the cumulative potential surface flux. This is just another way to show the same thing that we saw earlier. Here we have cumulative actual surface flux, but what is interesting is that then, and here you have the surface pressure head that of course changing dramatically from near saturation, so near zero, up to and goes beyond, much lower than the wilting point for corn, which was this is 80,000. So the consider that the wilting point was at minus 8,000. Okay, here we reach also a huge number until the threshold, which was the H criteria at which the evaporation, the potential evaporation then decreases to actual evaporation, because this is the threshold for at the soil surface for potential evaporation. But you can see that at the soil surface, the pressure head has a huge variability, of course, at the soil surface, not across the entire soil profile, especially when you go deeper, but potentially, of course, you don't reach these huge numbers, negative numbers, as long as you go deeper in the soil profile. But on the soil surface, there is a huge variability of pressure head values from zero near saturation up to the H criteria value. And so you can see the root zone pressure head, which is the mean of the pressure head across the root zone. So we said that we set the root zone from 0 to up 1.5 meters. And so you can see that the variation now it's much more narrow, and reaches the wilting point only in the last year, in some days. You see that, but every summer you can see that there are negative peaks every year, and so you get a very important reduction of potential transpiration. Okay, because the alpha changes becomes less than 1 already starting here at minus 800, I remember. No, at 300. We need to check again, and you see that the pressure, the mean pressure head over the root dramatically drops every summer up to minus 6,000 and so on. Okay, so that's why we expect to get a lot of root water uptake stress. Okay, this is the bottom pressure head. And finally, we get all the cumulative flux, all the fluxes, not cumulative, but here we get the cumulative fluxes. So if we add the legend, double click and we make it visible. So here you have the water budget. To put the legend probably here. I don't know if it's so much visible, but you can see that the black line is the top flux, the potential top flux, Okay, and the green line is the actual top flux, meaning the top flux, I remind you, that was precipitation minus evaporation. So for potential, the black line is precipitation minus potential evaporation, and the green line is precipitation actual evaporation. You remember that sometimes the evaporation got some reduction because the soil surface pressure had reached the negative, the lowest threshold value. I think it was 100,000 centimeters. And so there was some smaller reduction. But what you can see more interesting are the blue and the light blue lines, which represent the root water uptake. So the blue line is the potential transpiration, and the light blue line is the actual transpiration. So you see this gap? This is the water deficit after whatever 12 or 13 years, but you can easily calculate the deficit every year, okay? And we will see how. So this gap is very important in agronomic purposes because it tells you exactly the water deficit to fill the gap and to satisfy completely the potential water demand by transpiration. And the red line is the actual bottom flux, meaning the drainage that is expected and happens especially during the wet season. Okay, other results to show here. If we go bottom, you can see also if there was some runoff or cumulative surface runoff. Here you have the saltwater storage. The water storage is, of course, calculated by taking the mean of the water content values across the nodes, multiplied by the soil depth, which is 200 centimeters. And you can see the typical cycle. This is another nice variable, which is an integrated variable, depending, of course, on the mostly on the upper boundary conditions. Here we have also the cumulative evaporation. Of course, if you activate the heat transport, you can simulate also snow thawing, and so you can also add snow as precipitation. Okay, this is very important. Then you have the solute transport. We are interested in the nitrate, so we select the third solute, which is the nitrate, and click OK and visualize again the surface solute flux. You don't see anything because we, as an input, we put the fertilizer. At the bottom, yes, you have the bottom solute flux. So this is the nitrate flux happening at the bottom of our soil profile. And this is what concerns us, okay? This is the concern because this is all potential nitrate flux going down to the groundwater. And so you can see that there are some negative, of course, because it's always downward. And you have important peaks, especially in particularly wet seasons, when the rainy seasons you get more rain than normal, and so you get more higher intensity, a higher solute flux at the bottom of your soil profile. And here you can see it in terms of cumulative bottom nitrate flux, because we are talking about the third solute. And you can see here this breakthrough. So in this time, there was a particular concerning event, and here you have a sort of plateau. Probably the seasons were drier than normal, so so you get this kind of plateau stability. This is interesting. Oh, of course, you have also nitrate uptake by the roots, and this is a very another interesting plot, because roots absorb nitrate. You remember that we set up no solute stress for the nitrate, so we indicated 100 as fake number, very high numbers, the threshold basically, meaning that all the nitrate being concentrated in the root zone is partly absorbed by the roots during the root water uptake. And so this is another very, very important situation, because we can as well compare the concentration absorbed by the roots and the concentration that we effectively measured in the roots in the cornfields. So this information is very, very important, to my opinion. And of course also, and here you have the root solute uptake. If you want the concentration, you have the root solute uptake. If you want the concentration in the uptake, you have to divide root solute uptake by the root water uptake, and you will get the concentration of nitrates that were taken by the roots. Okay, I don't have so much time to go in the other options, but here you have quickly the water retention function, very nice. You can also show it in terms of, you can change the scale of the x-axis. So if you go to scale type, you can show it in logarithmic values. For instance, decimal logarithmic, you can see that the shape changes. And of course, you have to divide the divisions. It will be much less if you put 5 divisions. Okay, you get a nicer x-axis labels. And of course, you can increase or decrease the range. So you can start from 0, 1, for instance, up to the wilting point, for instance, or in the region of interest, also for plant, etc. So the most important thing that to show is to go into your directory to get the values, to get the output values. If you go in the working directory, you can see from my screen that there are like there is a list of text files. Okay, let me know if you see or if you have other questions, because this is very, very important, because you can take the output values from the output files. Okay, especially from these files, you can see that the files are input files if they end up in IN, and they are output files if they end up with dot out. Okay, it's very simple. If you go, for instance, to a level dot out, and if you open it to okay, now I should zoom. But if you select everything and copy paste into Excel, it will look much better. Go to Excel in a new spreadsheet, Control V, see if that happens. Yeah. And then you go to data in column, and if it's delimited, go on. Sorry if it's in Italian, but it's you just have to separate the columns because there is the space separator. So you need to separate the columns, and so you will see the output in a better fashion in Excel. So you have the water balance components here and some information on the pressure head on the soil surface, in the root zone, at the bottom of the soil profile in each day. Okay. Most importantly, it's also the T-level out. Same thing if you open it with the common text program, you do modify and select everything and copy. Another spreadsheet. You see that there is a much larger table. Oh, there is another question from Ines. What was the initial soil moisture conditions in the soil profile? Yes, in this question, so we set up not the soil moisture, but the pressure head as initial conditions from 100 at the soil surface, minus 200 over the soil surface at the bottom of the soil profile. And so you can see from the water content soil profile at time 0, you can see the corresponding water content values. In this file, so in the T-level.out, basically you take all the results that were showed here in the water flow, boundary fluxes, and heads. So as I said, there is the potential surface flux, and the first column is the potential surface flux. So you need to check, of course, you cannot write in a text file all the meaning, extended meaning, but circa R top. And so in the technical manual, if you search for R top, there is a table with all the symbols and acronyms. So for instance, R top is the potential top flux. Then there is R root, which is the potential transpiration. Then there is the V top, which is the actual top flux. And the V root, which is the actual transpiration. V bot is the actual bottom flux, and so on. These are the cumulative fluxes. These are the pressure head at the soil surface, the mean one in the root zone, and the and the pressure head at the bottom of the soil profile. Then there is runoff and cumulative runoff, if any, over the soil surface. Then there is the storage, the water storage called volume, and you can see here the units, the expected units. So mostly are in length units, and here is described the corresponding option that we selected. So its length is expressed in centimeter and time in days, and so on. But we have also the observation nodes.out. Again, select all, copy, and we go into another spreadsheet, paste, and here in the observation nodes, you have the pressure head. So you have the time for, the time is for all the nodes. And for each node, for instance, this is the first node at 50 centimeters. We have all the information So the pressure head, the water content, the flux, water flux, and the three concentrations. Basically, we have the nitrogen fertilizer, the NH4, and the nitrates, which are, of course, zero at time zero because we applied the first fertilizer on the 1st April of the first year, sorry for the, in 1999. And then we have again the second nodes. I use a different color. So this is the first node. And so on, okay? And here we have the third node. So what is important is that if we want to extract the simulated values at specific depth, we can go to observation, to the file, output file of the observation node, extract the pressure head, the water content, water flux, concentration values, and compare the simulations with the direct measurements. So that's why it is very, very important to deal with this file, okay? And then I show you the last important file, which is solute3.out. So if you open it again, same thing. There is all the information. Oops, sorry. All the information on the nitrates transport. And so you can see this again, the CV top is the solute flux over the soil surface. Then we have the CV bot at the bottom of the soil profile. Here we have the cumulative fluxes, solute fluxes. These two I don't remember actually. We need to check on the technical manual. But here we have the C top, C root, and C bottom, which are I remember very well because again we have the concentration at the top. So the nitrate concentration at the top, nitrate concentration in the root zone, and nitrate concentration at the bottom. Okay, this is another important different way. The CV root is the nitrate uptake by the roots, and this is the cumulative uptake. Again, if you want to estimate the nitrate taken by the roots, you have to divide CV root by the actual root water uptake that you take from here. Yes, here, by V root, this one, okay? So I repeat again, if you want to obtain the nitrate concentration taken by the corn, basically, you have to divide CV root by V root, these two informations, okay? And compare with your measurements. It's not C root, because C root is the concentration in the root zone, in the soil profile. Okay, this is another kind of information, but the CV root is the nitrate uptake as a flux. Okay, but if you want, usually we measure the concentration of nitrates into the plant, and so we need to divide CV root by V root. Okay, are there any other questions? Okay, I think we saw pretty much everything. Now we still have 15 minutes, so we can change something else. Hydrus 1D, everything is done. So basically, we can, for instance, make 3 layers. So we can increase realism. And if we go next, everything will be taken the same as before. Now we have to set up the Van Genupten parameters for each horizon, for each layer. You see that in layer number 1, you have specific Van Genupten properties. In layer number 2, we need to set the new properties. And of course, since we don't know anything about this mysterious soil profile, we're going to invent. And so in the second layer, we put a loamy soil. And in the third layer, we put a silty clay soil, okay? Just because there is no more time. So you can play by yourself or you can use your own data. It's much better if you measure the Van Genupten parameters, but if you can't, you can use Rosetta, for instance. So if you go next, that's what I wanted to show you. You can also trigger irrigation here. And if you trigger irrigation, a new window will pop up. So you can say, okay, when do you want to trigger irrigation? What is the criterion for triggering irrigation? So I say, okay, consider my first observation node, the one at 50 centimeters, and start irrigation when it reaches, I don't know, 500, minus 500 centimeters. And then at an irrigation rate of 1 centimeter per day, duration, let's say 1 day, and the lag time, let's say 1 day as well, okay? But if you go to in the help function, you can see all the details for that. The solutes will be exactly the same. So you see that now you have a table with 3 rows because the parameters, the reaction parameters for solute 1 have to be assigned for each layer, but they are the same for each solute and for each layer. So we need to extend this information here. Copy paste and keep everything else 0. And then next, so you can extend 3.5. So if you want to go deeper in these parameters, just check the technical manual because I don't have time to explain all the details, but these are reaction parameters. They tell you how the parameters react as a function of the gaseous phase or liquid phase or solid phase and so on. There are like also tortuosity parameters. Okay, so this one is okay. Anything else keeps the same here. Do you remember that we put the maximum allowed concentration for passive root solute uptake, and we put 100 for the third solute, which is nitrate. And so there is no stress for a root solute uptake. That's how the plant suck all the nitrate that stays into the soil. So they absorb nitrate with root water uptake, okay, without any filter. Okay, here remains all the same, and you can see that also the profile remains the same. I remember that to improve the solution of the Richards equation here, you can make it denser. But I don't want to go into details, and then you say, okay, save. and you press the green button. Now, I don't know if with all those changes, I don't know if it fails, but it's okay. Because even 2,000, 3,000 is a record enough to visualize the data. Let's wait until the end. Let's press continue, enter to continue. And let's go again to the observation points. And what you see is that it's a little bit different, isn't it? So do you remember that in the first simulation, the black line, so the pressure head at 50 centimeters depth was much lower. I remember that, right? And now it's much higher because of the triggered irrigation. Now we are buffering the water deficit. And so in the summer, there is irrigation. And so the pressure head gets higher, less negative, so especially in the root zone, etc. And so you can see also the impact on the water content cycle, and so on. But what is important is that you get here a new output file called irrig.out. So if you go to take your data, again, you open it with the text text. If you copy paste on Excel. Okay, here you have all the irrigation events across time. Okay, so you see that there are like there is the first event, the second event, the third event, and they tell you when. So in which days of the year they happen. So it happened here. So it was triggered at day number 138 and ended up at the following day. Okay, this is important because we can plot this information and we are in control of the irrigation supply each year because we just have to sum up, we just have to multiply the number of days in each year by the centimeters that we imposed as irrigation intensity, right? And so we know exactly the irrigation provided by the model. And this is a very important information. And then we can see, maybe just in the plot, because there is no more time, we can see the impact on the actual transpiration. Wait a second. Here, you see that the lines now are closer. We were almost able to fill the gap because we triggered irrigation just by using random values. It's not important. But by chance, we were able to almost completely fill the gap between the potential transpiration and the actual transpiration. It means that now the root water uptake demand was almost completely satisfied. And the stress is almost completely reduced. Okay? Probably the cumulative bottom flux increased a bit. I don't remember how much it was, but we can check easily because this is, let me check. So if we zoom up to Catch it. No. Oops. No. Now, by the way, it was around minus 300, and if the original one, cumulative V bot, is around minus 500, okay? Oops. So it was a little bit higher without the irrigation. Interesting. With irrigation, we get spray. Interesting. And the drainage was without irrigation, it was minus, almost minus 500. Okay, interesting. There's another finding. Oh, no, wait, maybe I checked the wrong column. This one. Okay, that's why I didn't see it. Oh, there you go. Without irrigation, it was the bottom flux, the drainage was minus 200. But when you add irrigation, of course, you have also more drainage. Okay, it makes sense. And it's now about minus 260 centimeters. But what's the point here is that when you irrigate more, you get more drainage and more migration of nitrates into the groundwater table. Okay, so this is like a game. So we need to play in order to reduce as much as possible the water stress, the root water uptake stress, but we need also to secure the drainage because more drainage means more nitrate bottom flux. Okay, so we need to play by triggering irrigation because we, of course, the plant will be, the potential transpiration will be reduced much less, but at the same time, more irrigation means more drainage, and more drainage means more transfer of nitrogen, nitrates down to the groundwater table. Okay, so I think it's enough. We are still 34 participants, so there was a hard selection, but probably most of you got sick or something. That's too much. I don't know if there are any other questions before we leave. I stop also the recording. In the meantime, sorry, because I